Hope you're doing well. Let's start our next section, that is data engineering. In today's data driven world, organizations across industries are recognizing the immense value of data. However, to harness the full potential of data, it requires robust and efficient infrastructure to process, transform, and analyze vast amount of information. This is where data engineering play a vital role. Data engineering encompasses the design, construction, and maintenance of the data architectures and systems that enable organizations to efficiently manage and utilize their data assets. This section explored the fundamental concept, tools, and practice involved in data engineering, highlighted its significance and the key challenges faced in building scalable and reliable data pipelines. So let's go through the table of contents. Introduction and importance of data engineering, foundations, data engineering lifecycle, tools and technologies, data quality and governance, real world applications, challenges, best practices and future trends in data engineering, and then we have our conclusion marks on data engineering. So now let's talk about the importance of data engineering. In today's digital age, data has become valuable assets for organization. Data engineering enable business to drive meaningful insights, make data-driven decisions, and build innovative products and services. It ensures that data is collected, stored, and processed efficiently, enabling faster, more accurate analysis. Effective data engineering enable organizations to unlock the full potential of their data assets, gain a competitive edge, and drive business growth. Data engineering involves the design, development, and maintenance of data systems and pipelines. It encompasses the wide range of tasks, include data ingestion, storage, transformation, integration, and processing as well. Data engineers work closely with data scientists, analysts, and other stakeholders to understand their requirements and build scalable and reliable data architectures. The scope of data engineers extended to various domains such as data modeling, database design, data governance, and infrastructure management. Foundations of data engineering. Data engineering versus data science. Data engineering and data science are complementary disciplines but serve different purposes. While data scientists focus on extracting insights and building predictive models, data engineers are responsible for the infrastructure and system that enable data scientists to perform their tasks efficiently. Data engineering lays the foundation for data science by providing clean, structured, and accessible data. Key components of data engineering. Data engineering involves several key components, including data ingestion, storage, transformation, processing, integration, and governance as well. Data engineers design and implement data pipelines that facilitate the seamless flow of data from various sources to its destination, ensuring its quality, consistency, and reliability throughout the process. Last, we have role of data engineer. They are responsible for end-to-end management of data infrastructure. They collaborate with stakeholders to understand data requirements, design and implement data architectures, develop data pipelines, optimize data processing workflows, and ensure data quality and governance. Data engineers also play a critical role in monitoring and troubleshooting data systems, ensuring their scalability, performance, and reliability. So next is, what is the life cycle of data engineering? First one, we have data ingestion. Involves acquiring data from various sources such as database, file system, APIs, or streamline platform. Data engineer designed ingestion process to extract data reliability, validate it, and load it into a storage system for further processing. Data storage. Data storage involves determining the appropriate data storage system based on the organization requirements. This may include traditional relational database, distributed file system, columnar database, data warehouses, data lakes, and etc. Data engineers consider factors such as data volume, velocity, variety, and assess patterns to select the most suitable storage technologies. Data transformation involves cleaning, enriching, and reshaping the data to meet the specific needs of downstream applications. Data engineers use tools and techniques such as data wrangling, data integration, and data normalization to ensure data consistency and quality. Data integration. Data integration involves the combining data from multiple sources into a unfilled view. Then they break design integration process to handle data from disparate sources, perform data deduplication, handle schema evaluation, and maintain data consistency across different systems. Then we have data processing. Involves performing computations and analytics on the transformed data. Data engineers design and implement data processing workflows using technologies such as batch processing framework. For instance, Hadoop, MapReduce, or stream processing frameworks such as Apache Spark or Apache Flink to drive meaningful insights in real time or batch mode. Last, we have data governance. This includes defining policies, processes, and standards for data management, ensuring the quality, privacy, security, and compliance of data. Data engineers collaborate with stakeholders to establish data governance framework, implement data lineage and metadata management systems, and enforce data protection practices. Our next segment is building scalable data pipelines. Batch processing versus stream processing. Data warehouse and data lakes are common architecture patterns for storing and managing a large volume of data. Then engineers design and implement these systems using technologies such as relational databases, distributed file systems, or cloud-based storage services. They consider factors such as data access patterns, scalability, cost, and data retrieval performance. Now we talk about ETL, extract, transform, load processes. ETL processes involve extracting data from source system, transforming it to fit the large schema, and looking it into the destination system. Engineers such as data engineers design and optimize ETL workflows to ensure efficient data movement and transformation. Consideration factors such as data volume, complexity, and latency requirements. Last one, we have cloud-based data engineering. Cloud computing has revolutionized data engineering by providing scalable and cost-effective infrastructure. Data engineers leverage cloud platforms such as Amazon Web Services, AWS short form, Microsoft Azure, or Google Cloud Platform (GCP) to build and manage data pipeline, storage, and processing systems. Cloud-based services provide flexibility, scalability, and automation capabilities, enabling organizations to focus on data engineering rather than infrastructure management. Now we discuss some of the important tools and technologies. First we have Hadoop ecosystem. The Hadoop ecosystem comprises various open source tools and frameworks including Hadoop Distribution File System (HDFS), MapReduce, Hive, and PAG. Data engineers use these technologies for distributed storage, batch processing, and querying large datasets. Second, we have Apache Spark. Apache Spark is a powerful data processing engine that supports both batch and stream processing. Data engineers leverage Spark for its in-memory computing capabilities and capacities, fault tolerance, and rich APIs, enabling faster and more efficient data processing and analytics. Then we have Apache Kafka. Apache Kafka is a distributed streaming platform that enables real-time data ingestion, processing, and messaging. Data engineers use Kafka to build scalable and fault-tolerant data pipelines, ensuring reliable and efficient data streaming across the applications. Then we have Apache Airflow. Apache Airflow is an open source platform for orchestrating and managing data workflows. Engineers use Airflow to schedule and monitor data pipelines, define dependencies between tasks, and handle workflow failures and retries. Moving on, we have stream processing frameworks. Like Apache Flink and Apache Storm enable data engineers to process and analyze continuous streams of data in real time. These frameworks provide low latency processing, fault tolerance, and support for complex event processing. Last, we have data integration tools. Data integration tools such as Apache NiFi and Talend simplify the process of data ingestions, transformations, and integrations. The tools provide visual interfaces for designing data workflows, managing data dependencies, and handling data quality and validations. Next, we move on to data quality and governance. Data quality management involves ensuring accuracy, completeness, consistency, and timeliness of data. Engineers implement data quality checks, validation rules, and data profiling techniques to identify and resolve data quality issues. They also establish data quality monitoring processes to proactively detect and address data anomalies. Next, we have data lineage and metadata systems or management. Data lineage and metadata management enable organizations to understand the origin, transformation, the base, and usage of data throughout its life cycle. Data engineers implement data lineage tracking mechanisms and metadata repositories to capture and document data transformations, dependencies, and associated metadata. Last, we have data security and the privacy. Data engineers play a critical role in implementing data security and privacy measures. They ensure that sensitive data is protected across control in place, encryption is applied where necessary, and data anonymization techniques are employed to preserve privacy. Data engineers also adhere to regulatory requirements such as GDPR or CCPA to ensure compliance with data protection laws. Real world applications of data engineering. First, we have to discuss about IoT, Internet of Things, where data engineering plays a vital role in managing the massive amounts of data generated by IoT devices. Data engineers design and implement data pipelines to ingest, store, and process sensor data, enabling real-time monitoring, predictive maintenance, and intelligent decision-making in IoT applications. Machine learning and artificial intelligence. Data engineering provides the foundation for ML and AI initiatives. Data engineers pre-process and transform data, create training datasets, and optimize data pipelines to support ML models, training, and interference. They ensure that the right data is available in the right format at the right time to enable accurate and efficient model development and deployment. Real-time analytics. Data engineering enables real-time analytics by processing and analyzing data streams as they arrive. Real-time applications such as fraud detection, recommendation systems, predictive analytics rely on data engineering to ingest and process data in real time, providing instant insights and actionable information. Last but not the least, data-driven decision making. Data engineering empowers organizations to make data-driven decisions by building scalable and reliable data pipelines. Data engineers ensures that the decision makers have access to accurate and up-to-date data. They enable the integration of disparate data sources, perform data transformations, and provide analytics-ready data, enabling stakeholders to make informed decisions based on reliable insights. Now let's talk about some challenges. Data volume, velocity, and variety. The exponential growth of data poses significant challenges in terms of storage, processing, and management. Data engineers must design scalable and efficient architectures that can handle large volume of data in real time while also dealing with diverse data formats and resources. Data integration and compatibility. Integrating data from different systems with varying formats and structures can be complex. Data engineers face challenges in harmonizing and transforming data to ensure compatibility and consistency across different data sources. Data quality assurance. Ensuring data quality is a critical in data engineering. Data engineers must implement data quality checks, validation rules, and cleaning processes to address issues such as missing data, duplicates, and inconsistencies or inaccuracies. Data governance and compliance. Data governance and compliance are vital considerations in data engineering. Data engineers must ensure that data is handled in accordance with regulatory requirements and organizational policies. They need to establish data governance framework, implement data security measures, and enforce data access controls. Last one, we have scalability and performance. Building scalability and performant data pipeline is a challenge. Data engineers must optimize the data processing workflows and flowcharts, select appropriate technologies, and implement distributed computing techniques to handle increasing data volume and deliver timely insights. Now discuss some of the best practices in data engineering. Data modeling and schema design. Data engineers should follow best practice in data modeling and schema design to ensure data consistency, efficiency, and ease of use. They should understand the data requirements, normalize or denormalize data structures appropriately, and consider future scalability and flexibility. Code reusability and modularization. Data engineers should adopt modular and reusable coding practice to enhance productivity and maintenance. They should develop reusable data transformation functions, libraries, workflows, and reducing duplication and promoting code consistency. Data pipeline monitoring and alerting. Monitoring data pipeline is crucial to ensure their reliability and performance. Data engineers should implement monitoring solutions that provide visibility into pipeline health, data flow, and processing matrices. They should also set up alert and notifications to proactively detect and address issues. Version control and collaboration. Version control system and collaboration tools play a vital role in data engineering projects. Data engineers should adopt practices like code versioning, code reviews, and collaboration platforms to facilitate teamwork, maintain code integrity, and track changes effectively. Last, we have continuous integration and deployment, short form CI or CD. Implementing CI or CD practices in data engineering enables automation, agility, and faster deployment cycle. Data engineers should establish CI/CD pipelines to automate testing integration, deployment of data pipeline, reducing errors, and performing and promoting efficient delivery of data solutions. The next module is future trends in data engineering, data operations, and dev operation integration. An extension of dev operation principles to data engineering emphasizes collaboration, automation, and agility in data workflows. The integration of data ops and data DevOps practice will streamline data engineering processes, enable faster delivery, improve quality, and better alignment between development and operation terms. Serverless computing abstracts the underlying infrastructure, allowing data engineers to focus on building data pipelines without worrying about infrastructure management. Serverless architectures provide scalability, cost efficiency, and simplified deployment, making it emerging trend in data engineering. Data mesh architecture, decentralized data ownership and management enable domain-oriented data terms to take ownership of their data products. This approach promotes data decom- democratization, scalability, agility, allowing data engineers to build self-serve data infrastructure and services. Streaming analytics and complex event processing. As real-time data becoming increasingly important, streaming analytics and complex event processing technologies are gaining traction. Data engineers will need to develop expertise in streaming platforms, event-driven architectures, and real-time analytics frameworks to handle continuous streams of data effectively. Last future trend is automated data engineering. Automation will play a significant role in data engineering, reducing manual effort and improving productivity. Data engineers will leverage technologies like machine learning, artificial intelligence, and intelligent automation to automate repetitive tasks, optimize data pipelines, enhance data quality, and governance processes. So, our concluding remarks on data engineering is that it is a critical discipline that empower organizations to unlock the value of their data assets. By designing and building scalable data architectures, data engineers facilitate efficient data processing, transformation, integration, and governance. They play a vital role in enabling data driven decision making, real time analytics, and the success of machine learning and artificial intelligence initiatives. As the data landscape continues to evolve, data engineering will continue to evolve, embracing new technologies, practices, and approaches to unleash the power of data and drive business innovation and growth. So that's the end of this module. I hope you guys understands all the important concepts, theories, and key terms related to data engineering. If you have any questions, feel free to ask me anytime. I'm always here to help you guys. Take care, have a good day. See you in our next coming lecture.